Okay, welcome to this third of our tutorials on functions, and for this one we will consider creating inverse functions. If you've missed any of the previous ones, then you should find a link popping up on the screen for those if you need to catch up. Inverse functions, working backwards. We're going to start with a very simple one just to illustrate our methods and the point. And here we have double and add 3 is the instruction for the function. Our domain, let's use a very small domain of 1, 2, 3, and the range, the answers that come out of this would be 5, 7, and 9. The inverse function, well, many people will tell you that if you double something and then you add 3, fairly obviously to go backwards you must minus 3 and divide by 2. So we have an inverse function of, and the notation we use this superscript of -1, we minus 3 and divide by 2. And interestingly, and this is a key point with inverse functions, is that the range now becomes the domain. So the domain and the range become exactly opposite. And what we see is we see this. So the swapping of the range and domain is very key to what goes on with an inverse function. What went in now comes out, and what goes out now goes in, and it also gives us a slightly better method than this flowchart type method. The method that we'll generally use to create an inverse is 2 steps. We will first of all write the function as y equals. So first step, we write y equals, and the second step is to simply switch the range and domain. That is to say, x becomes y and y becomes x. So we simply swap all the x's and y's, range for domain and vice versa, and then we have an inverse function. We need to go a little bit further to make sense of this. And if y is made the subject, then we have our inverse function. And so there we are. We swap our range and domain and we make y the subject. That's what we do to create an inverse function, and it works every time. And it works for all sorts of weird and wonderful functions. Let's just have a couple of examples for this just to cement the idea. F of x equals there we go. So the method y equals, there's our function, and the method is swap range for domain, x becomes y, y becomes x, and make y the subject. Subtract 1, multiply by y, divide by x minus 1, and we have our inverse function there we go. Here's an awkward one that crops up quite often, or at least rational functions can provide problems. Rational functions are functions that appear written a little bit like fractions, like this. There's a nice rational expression, and no difference in the method, but we've got to be a little bit careful with this one. You'll see something happening. So if we start off with y equals and if we then swap the range for the domain, swap the x's and the y's, and now making y the subject, this is the difficult bit of this particular question. We have y appearing twice. Now this is one of those tricks that once you've seen once, you can usually duplicate again. What I'm going to do is I'm going to multiply by the y minus 5. I'm going to multiply out this bracket. And to deal with it now, we still have y appearing twice, but I'm going to collect all the expressions with y in on one side of this, and I'm going to leave all other expressions on the other side, and the trick is to create a bracket, a factor. When we do that, magically y appears on its own. We can divide by x minus 1, and we have our answer. There we go. Our inverse function is there, and bingo, we've got it. Now I'm just going to pull up a diagram of some inverse functions that will illustrate a particular point that is worth noting. This idea of swapping range for domain. You'll remember that the domain appears as the numbers in on the x-axis on a graph, and the range the y-axis. Now if we swap those over, if you swap the x's for y's, the range for domain, what goes in comes out, then you see this particular setup here. If we look at another function, you'll see other things. You'll see something in common. The blue is the function, the red is the inverse, and you will notice that for all these we seem to have something very particular going on. The idea is that if we swap x for y, y for x, swap the axes over, we simply reflect. We're going to reflect everything in the y equals x line, which kind of makes sense if we think about it. What goes in comes out, and what comes out goes in, and it just all swaps over. So there we go, that's y equals x cubed and the cube root of x. That's one that we did a minute ago, but we see a symmetry there. We see it reflected in y equals x to create the inverse. Here's an interesting one. This is what we call a self-inverse function, where the function itself takes it back to where you started, 1 over x back to where we started at x, and of course if we do that the reflection doesn't appear. The reflection lands right on top of the original, and the symmetry of this, the fact that it's symmetrical in y equals x, tells us that it's a self-inverse function. There's one, that's that complicated one we did a moment ago, and we can see that one, certainly not self-inverse, but we can see a perfect reflection once again in that. So swapping the range and domain, y's become an x's, x becomes y, creates a reflection in the line y equals x, and it's a neat way to see on a graph if you've got an inverse function. Let me put that away again. Knowing if you've got an inverse function. Last thing we'll say is a quick test. So if we have a function, and I've just got ahead of myself there. If we have a function, let's say 5x plus 2, and if we look at the inverse function of that, which is going to be x minus 2 over 5, a neat way to check an inverse function, well, we could put numbers in. For example, if we put the number 3 in, if we send it through f, 15 plus 2, 17. and send it through the -1. Lo and behold, -2 divided 5 gets us back to 3. It's what we expected. And if we use f to the -1 first and then f, we will see exactly the same thing happening. Whatever number we put in will come out. And this provides us with a bit of a check for inverse functions, in that if we create a composite f of f to the -1, or indeed f to the -1 of f, then we should be able to see whether we've got the right inverse. Let's try this one first. So going through f to the -1x first, going through the inverse, we see this, and then taking this expression through f. Remember, it's not about the letters here. F tells us to multiply by 5 and add 2. So f of this is multiply by 5 and add 2. See what happens here. And lo and behold, exactly what we expected for an inverse function. If we put x in, go through the inverse, go through f, then we will get x out, and we can test it, but exactly the same thing will happen with this one, and we know we've got our inverse. Okay, so inverse functions. What we have is we have a method which you should be aware of, and the method to use here is y equals, then we swap x for y, and then we rearrange. That's our method to create an inverse function. We have some key points on the graph. We will see a symmetry, and that symmetry will be in the y equals x line. So we've got a method, we've got a very key point on the graphs, and we've got a variety of checks, one of which is that f to the -1 of f is going to give us the same result as f of f -1x, which will always give us the x, and that is our check, and that is our inverse functions.